Okay, welcome to lecture number 3. Today's first topics is in section 1.7, reliability of measurements. Reliability of measurements is important in science because, well, we always strive for the greatest accuracy possible. Every measurement done, no matter how carefully you do it, and no matter how sensitive the measuring instrument you're using, will always have a certain amount of error in it. Your goal is to minimize the error. And one way that you can minimize the error in measurements is reading all of the digits that are available in a measurement. That is, use your measuring device to the fullest extent possible. Because the more digits you read, the more reliable the measurement probably is. So the number of digits in a measurement is related to the accuracy with which it's known. And generally, for the most part, assuming that you're being careful about things, more digits in an answer means more certainty in the answer, and fewer digits would mean less certainty in the answer. And when you're taking a measurement, what you will normally do is record all of the digits that are known with certainty. And the first uncertain digit. And the first uncertain digit is uncertain because that would be a digit in which you've estimated. And so what we usually do is we measure to the smallest increment. I'll do that again, increment on the measuring device, and estimate one place beyond that. And because we estimate the last digit in any properly taken measurement, we generally assume that the last digit reported for any measurement is uncertain by plus or minus 1. And so, for example, if you're measuring something with a normal metric ruler, well, on most metric ruler, the smallest unit would be millimeters. And what you're going to do is read to the certain number of millimeters and then estimate to the nearest tenth of a millimeter. Because when you're doing a measurement, it's quite likely that the object you're measuring will not fall exactly on one of the lines for the measuring device. So if you're measuring the length of, I don't know, a piece of paper, it's not very likely that the paper is going to fall exactly on one of the lines on the ruler. It's going to fall between two of the lines. So you read the lines as far as you can, but then when you get to the point where the paper or the edge of the paper is actually between two of the lines, you kind of have to estimate how far between the two of the lines, and that will be the final digit, the one that we assume to be uncertain by plus or minus 1. So, for example, (32.2) means 32.2 plus or minus 0.1. We're assuming that that 0.2 was estimated. So we're assuming that that last digit could be one higher or one lower. And in other words, what that means is you could have a range of anywhere from 32.1 to 32.3 for that reading. That allows for differences of opinion because you're estimating that last digit. Other people may disagree. And so what we're doing by assuming that it's uncertain by plus or minus 1 is we're leaving room for different people to read it a little bit differently than you do. And if you had just recorded that reading as 32 and not tried to estimate the 10th place, what 32 actually means is 32 plus or minus 1. We assume that that last digit is uncertain by plus or minus 1. That would be a range of anywhere from 31 to 33, which is a much broader range than what we have up here. So by estimating that last place to the 10th place, we've actually made the reading quite a bit more accurate than it would have been otherwise. Okay. So, but normally the number of digits that you would report for a measurement would depend on the measuring device. And I'm not going to go into a huge amount of detail on that just because this is an online course, so we're not actually going to be measuring anything in here. We may say more about that in the lab portion of the course, but not in the lecture. So we'll talk about it over in the lab if we need to. Okay, further related on this topic would be the subject of significant figures. Significant figures are meant to help us understand how accurately we know a number from a measurement, and to help us maintain that level of accuracy through calculations so that we don't end up thinking that we know the result of a calculation more accurately, or in some cases less accurately than we really do know it. So if you take track of the significant figures in all of your measurements, you'll know how accurately you know them. And then when you take those measurements and use them in calculations, you will know how accurately you actually know the result of that calculation. It's important for us to be aware of significant figures and how to count significant figures, because unfortunately calculators are not programmed to recognize significant figures. So a lot of times your calculator will spit out a number that has 10 or 12 digits in it, when according to the rules of significant figures, your answer should really only have maybe 3. And so a 12-digit number would imply that you know the answer a lot more accurately than you really do. And we want to avoid that, because all of those extra digits beyond the ones that you're actually allowed to have according to the rules of significant figures, all those extra digits are fake, basically. They're digits that you don't really know. Okay, so significant figures, they help preserve precision of instruments and calculation. And you want to keep track of them to avoid We want to basically keep track of them to avoid thinking that we know a number more accurately than we really do. So generally, when we're doing any kind of measurement or reporting any kind of number, the greater the number of the significant figures, and I'll start using this abbreviation right away because I use it all the time. Sig figs is a common abbreviation for significant figures, so don't be too confused when you see that. The greater number of significant figures generally means greater certainty. Now, before we can do anything with significant figures, we have to know how to recognize significant figures and how to determine how many there are in a given measurement. So under counting significant figures, first you need a number of whose significant figures you want to count. And there are a couple of rules. Of course, there are always a couple of rules in chemistry. First is that non-zero digits always count as significant. Okay, so if it's not a zero, it'll definitely be significant. The zeros are the troublemakers, because some zeros are significant and some are not. So zeros at the beginning of a number are never significant. So when they have zeros at the beginning of a number, they're really just there to show you where the decimal point is. And it's easy to write the same number in different ways, like in scientific notation, without those zeros at the beginning. And you know the number just as accurately, but the zeros aren't there. So those zeros at the beginning of the number, like I said, they're just there to locate the decimal point. And so they're not significant. They have nothing to do with the accuracy of the number. If they come between non-zero digits, they are always significant. So if a zero has numbers on either side of it that are not zeros, then that means not that it is significant. A zero at the end of the number, oh, this is where it really gets fun. Let's see, significant if there's a decimal point. Somewhere in the number. They're not significant if there's no decimal point in the number. And that decimal point could be anywhere in the number. The zeros could be at the end of the number, and the decimal point could be way back at the beginning of the number. But if there's a zero, or if there's a decimal point anywhere in that number, then the zeros at the end are significant. Okay, so that decimal point could be anywhere. But if there's no decimal point, actually, if there's no decimal point, then it's kind of ambiguous as to whether the whether the whether the zeros at the end of the number are significant or not, but we generally try to play it safe by assuming that they're not. We go generally with the smallest number of significant figures possible. And that situation can be avoided with scientific notation. For instance, the number 180 could have two significant figures. In fact, that's what we would normally assume, because like I said, we generally go with the smallest number of significant figures to be safe about it. Or it could have three, depending on how you did the measurement and how accurately you actually know the number. Maybe you just forgot to put the decimal point at the end, indicating that it has three significant figures. So you could avoid ambiguity by writing either 1.8 times 10 to the second, which is 180 with two significant figures, or 1.80 times 10 to the second, which would be 180 with three significant figures. So you see, that way you can make it clear. Okay, so we were just about to, we were just going over significant figures and how to count them. And as I was saying, the zeros are the hard part. So that's what you have to watch out for when you are counting significant figures. We'll do some examples in a little while. But another factor you have to watch out for when counting significant figures is exact numbers. Exact numbers are numbers that you get from counting, say, separate objects. Like saying the carton contains 12 eggs. 12 is an exact number. It doesn't matter whether the eggs are big or little. You don't count it as a fraction of an egg. If it's a small one, it's either an egg or it isn't. So when you say there are 12 eggs, that means exactly 12. And that means infinite significant figures, 12.0000 on to infinity. So actually, that number could be considered infinite in terms of significant figures. Or these numbers can come from definitions or exact relationships. Or they can be from integers in equations. Because these numbers are known exactly, there's no uncertainty associated with them. And that's actually considered to be an infinite number of significant figures. So for example, like I was saying, if the carton contains 12 eggs, that's considered to be infinite because it's from counting separate items. And that would be considered 12.000 on to infinity. 1 yard is equivalent to 3 feet. That's a definition in mathematics. And so that would be considered 3 exactly, 3.000 on to infinity feet. Conversion factors within the metric system, or sorry, within the English system, that is relationships between different measurements in the English system, are considered to be exact numbers. And so those are considered to have an infinite number of significant figures. Relationships within the metric system are also exact. So when we say 1 kilometer is equal to 1,000 meters, that is considered to be an exact number. It's 1,000.000 on to infinity. Another one would be, say, say radius is equal to diameter over 2. That 2 is an integer, which means it's an exact number, and that would be considered to be an infinite number of significant figures. 2.000 on to infinity. Okay, so those are kind of exceptions to the rules of counting significant figures. And so as a little bit of practice to determine the number of significant figures, I'll lay out some numbers here. Okay, 5,547 kilometers, 7 pennies, 1.01 times 10 to the 5th meters, 0.00099 seconds, 1.4500 kilometers, and 21,000 meters. So if we're going to be doing significant figures with these numbers, you can feel free to pause the video and look back at the rules to try to come up with the number of significant figures before I actually give you the answer in each case. In fact, that's probably the best way to do it. There will be more practice in homework problems and things like that too. So 5,547 as a number is not really difficult because there are no zeros in it. So all of the digits count. So that would be 4 significant figures. 1, 2, 3, 4. 7 pennies. Notice pennies are something that you would count, and you generally don't consider, say, a penny that maybe has a little nick in it or something to be any kind of fraction of a penny. It's either a penny or it's not. And so 7 pennies would be a number from counting separate items, and that's infinite. That would be exactly 7, 7.0000 on to infinity. Okay, 1.01 times 10 to the 5th. It has a 0 in it, so that's what you sort of want to focus on. The 0 is between numbers that are not zeros, and so that counts. So there are 1, 2, 3 significant figures here. .00099, on the other hand, has zeros at the beginning of the number. And remember, zeros at the beginning are only there to locate the decimal point. They don't count as significant. So only the 9s count as significant in this number. The zeros don't. On the other hand, the 1.4500 kilometers has zeros at the end. Remember the distinction for zeros at the end. They count as significant if there's a decimal point, and if there's no decimal point, then they're not significant. Well, there actually is a decimal point in this number. It's way back at the beginning, but that still counts as a decimal point. So those zeros are significant. And we have 1, 2, 3, 4, 5 significant figures. 21,000, on the other hand, notice there's no decimal point in this number. So the zeros at the end do not count. And so only the first 2 digits do, the 2 and the 1. That's 2 significant figures. If we had 21,000 with a decimal point at the end, or anywhere in the number for that matter, then we would have 1, 2, 3, 4, 5. That would be 5 significant figures. Okay, now that we've know how to count significant figures, the next point would be to do calculations with significant figures. I see by my timer here, though, that I'm up against a half hour for this part of the lecture. So I'm going to cut this off, and we'll continue with the next part B, I believe.